Hello, everyone. I hope you all are doing good. We are going to cover week 2 of statistics for social sciences. Let me share the file. Okay, chapter 2 is about graphing distributions. When we think about graphing distributions, we need to think about qualitative variables and quantitative variables separately. Okay, so for quantitative variables, we have several graph types, such as stem and leaf displays, histograms, frequency polygons, box plots, bar charts, line graphs, and dot plots. Okay, so graphing data is very important. But why? Because we would like to summarize the data so people can understand it better. Okay. Let me start with the qualitative variables. Okay. Okay, here is an example. Apple Computer introduced the iMac in August 1998. The company wanted to learn whether the iMac was expanding Apple's market share. Was the iMac just attracting previous Macintosh owners? You know, the iMac, it is a special machine, so they just would like to know whether, the iMac owners, I mean, the Macintosh owners may prefer iMac better than other computer users, okay? Or there are some new buyers, right, who didn't own Apple before, okay? So to find out this research question, what they did, they interviewed 500 iMac customers. Okay, so each customer was categorized either as a previous Mac owner, okay, previous Windows owner, or new computer purchaser. Okay, so let's see the categories here. Okay, when you look at the frequency table, which is shown in table 1, okay, so out of 500 people who purchased iMac, 355 is previous Mac owners, okay, which amounts to almost 70%, okay. About 60 were Windows users, so 12%, and 17% didn't have any computer before. Okay, so this is the frequency table for this data set. Okay, what we can do, instead of frequency table, we can put this data in pie charts. Okay, in a pie chart, each category is represented by a slice of a pie. Okay, and then which is going to be proportional, right, to the percentage of responses. So who will have the biggest share? The biggest share will be, we belong to Mac owners, right, 71%, and then 17% didn't have computers before, and 12% were Windows users. You see, pie charts, they are really easy to read. Okay, so this is the pie chart. So pie charts are really effective for displaying the relative frequency of small number of categories. This is really important, small number of categories. They are not recommended, however, when you have a large number of categories. It means if you have like 10 categories, so pie chart is gonna be a mess. Okay, so when you have fewer number of categories, pie chart is really preferred. Okay, let's look at the bar charts. We can put the same data. on the bar charts. Bar charts are also easy to read, So this is the number of buyers. It's going to be on the y-axis, okay? And then the categorical variables, previous computer, is going to be on the x-axis. So as you see, Mac owners have the largest share, okay? Followed by the ones who didn't have computer before, and the Windows users were the last. Okay. So if you want to compare two distributions, then in that case, it is better that you draw a bar chart. So bar charts are often excellent for illustrating differences between two distributions. Okay. Here is another example. Let me see. You see, I think people, they play some card games on different days, either Wednesday or Sunday. As you see, Wednesday is marked in blue, and then Sunday is marked like, not yellow, let's say yellow, no problem. And then as you see in the spades, people played more, right, on Wednesday. Whereas in like cribbage, people played again more on Wednesday. So you can see the trend when you look at the bar chart like this. It's easy to read. Okay. They cover some graphical mistakes to avoid. Most of the time some people would like to cheat people or to deceive people. So they put like different kinds of scales, like the three-dimensional version of figure 2, which is not very easy to read. I wouldn't recommend that. Okay. Or you can put something like this. You see the factor, the Mac, has the biggest share, but you see the size-wise, I think they are not proportional. So there is a distortion. Okay. Like this one, again, previous computer, number of buyers. You see the baseline is 50. When you put the 50, the Windows is almost not existent. So these graphs are not really good to represent the data. Okay. If we summarize the charts for the qualitative data, we can say pie charts and bar charts are both effective methods for portraying qualitative data. Bar charts are better when there are more than just a few categories and for comparing two or more distributions. And then we should be careful to avoid creating misleading graphs. So it means when you have a qualitative variable, you have two options basically. Either you draw pie charts or bar charts. When you have quantitative variables, you have several options. Actually, you have many options, I would say. Stem and leaf displays, histograms, frequency polygons, box plots, bar charts, line graphs, and dot plots. Okay, so when you say a variable is quantitative, it means it is measured on a numeric scale. So we have numbers, right? Some examples are like height, weight, response time, subjective rating of pain, temperature, and score on an exam, etc. Okay. Let's begin with stem and leaf. Here, there are 31 teams, and then those are the number of touchdown passes. So the basic idea in stem leaf plot, what you do, you basically put, like when you have 37, so you put 3 here, and then 7 here. That is the idea. When you have 21, you put 2 and 1 here. When you have 18, you put 1 and 8 here. So you have a stem part, and you have the leaf part. So that's why it's called stem end. leaf plot. Okay. Display. Let's see how they did it. You see, you have 0, 6, 9. Okay. 1, 2, 2, 2. You see the basic idea, you can see the trend here. Like when you think about the distribution, you have a distribution like this. That's why stem and leaf plot, they really kind of show where the distribution stands. Okay. Exactly. One purpose of a stem and leaf display is to clarify the shape of the distribution. Okay. We can even make our figure more revealing by splitting each stem into two parts. Okay. What it means, up to 34, right? You get one stem and leaf. After 35 and more, you get another stem and leaf. So as you see, you have 37, 32, 33, 33, 28, 28, 29, 20, 20, 21, 21. It goes like this. You see, you can see the data better when you have kind of split. You have split the data. So that is the stem and leaf, but the data are split into two parts. That's a great way of showing the trend. It's called back-to-back stem and leaf display. Okay, so it means you have one distribution here and then another distribution here. So if you want to compare the distributions, it is better to draw back-to-back stem and leaf display. Okay. I think the left side is for 1998 and the right side is for 2000. Those are touchdown data for American football. Okay. You see the trend is pretty similar, except for like here, there is a difference like in this part. And then the rest is very similar. Those are some different examples. You see the same idea, 43, 43, 36, 21, 10, 10. Okay. So you have minuses here. So in the minus scale, you have the same idea, same logic to follow. Okay. Those are just the variations of stem and leaf display. Okay, histograms, important especially for continuous data. Histogram is graphical method for displaying the shape of the distribution. It's particularly useful when there are a large number of observations. You see, when you have large number of observations, you may use histogram. Okay. You see, in the histogram, what is happening? You don't have exact the values. What you have is an interval. So like this interval starts from 39.5 and ends in 49.5. So how many data points are there? 3. So 10, 53, 107, 147. It goes like this. So what you have, you don't have the individual y values. You have the interval. So you basically lose your data points. You basically lose individual data points. Okay. So when using histograms, the real question is how many classes should we have? How many classes should we have? We have different formulas in the literature. Okay. Let me see what is given here. Okay. Like some rules of thumb that can help you choose an appropriate width. Okay. One of them is Sturge's rule to set the number of intervals as close as possible to 1 plus log 2n. So n is the number of data points. Data points. Let me do the math for you. Let's assume you have just 16 data points. Then what you do, you just put here log 2 16, and then this will give you the value of 4. 1 plus 4 will give you 5. So you will need 5 classes based on this formula. Okay, if you use this one, that's what you will be getting. Okay, there is another rule called Rice rule. It is twice the cube root of the number of observations. Cube root. So like this times 2 will give you number of classes. Let's do the math. Let's assume you have 27 values. You put 27 here, then you will get 3. 2 by 3 will give you 6. So you will need 6 classes by using this Rice formula. Okay, so the best advice is to experiment with different choices of width and to choose a histogram according to how well it communicates the shape of the distribution. That's kind of the bottom line. Okay. So when you use a different formula, you will have different number of classes. Okay. Frequency polygons. Those are also graphical devices for understanding the shapes of the distributions. Okay. They serve the same purpose as histograms, but are especially helpful for comparing sets of data. Frequency polygons are also a good choice for displaying cumulative frequency distributions. Okay, so you will have a class interval in that case too. As you see, so that's the lower limit, upper limit count, and cumulative count. When you have cumulative, it means you add the values up. 0 plus 3 will give you 3. So 3 plus 10 will give you 13. 13 plus 53 will give you 66. It goes like this. So that's the cumulative count. Okay. Let's see a frequency polygon. As you see it starts like this. That's the test score. Okay. And then those are your frequencies. So that's the frequency polygon. Okay. Also, you may have a cumulative frequency polygon for the same test scores. Of course, the shape is going to be different. Since it's cumulative, it goes like this, and then at the very end, you will have n, right? The total number of observations. So that's the cumulative frequency polygon. So they are useful for comparing distributions. Okay, so in that case, you see overlaid frequency polygons. This is for the large target, and this is for the small target. So you can make comparisons easily. And this is the cumulative frequency part. Right now, you know the difference. That should not be a big deal. Box plots, very, very important concept. Very, very important concept, the box plot. I'll kind of make this part a little bit easier to understand for you. They are really useful for identifying outliers and for comparing distributions box plot. Okay. For the box plot, you need basically 5 values. You need the minimum, you need the Q1, 25th percentile, you need the Q2, median, 50th percentile, you need the Q3, which is going to be 75th percentile, and then you have the maximum. Okay? Most statisticians suggest if there is no potential outlier in your data set, that's how you draw the graph, box plot. So you have the minimum. So you start with the minimum. You go to the Q1. Then you go to the Q2, which is the median. You go to the Q3, and then you extend the graph to max. So when there is no outlier, that is the basic shape. So how can I understand whether there is a potential outlier or not? So if you have a potential outlier can be here or here, like on the left side or on the right side. The basic idea is you need to find the interquartile range first, which is IQR. So IQR is equal to Q3 minus Q1. Okay. So when you have Q3 minus Q1, you will get the IQR value. So what you do, Q1 minus 1.5 times IQR is your lower limit. And then Q3 plus 1.5 times IQR will be your upper limit. So in your data set, if you have a value which is smaller than this one, it's a potential outlier. Or when you have a value which is larger than this one, it's a potential outlier. So when you see the potential outliers, then you need to draw the box plot accordingly. I'll show you how you can do it. Okay. So for women's time, right? Women's times, 25th percentile 17, 15th percentile 19, and 17th percentile is 20. And let's see, for the men, I think the data is not shown, but let's focus on the woman side. So when you have a scenario like this, right, then what's going to be IQR? So IQR will be Q3 minus Q1, which will give you 20 minus 17, 3. So IQR is 3. So let's get the lower part, lower limit, Q1 minus 1.5 IQR. So Q1 is 17 minus 1.5 times 3. Okay, let me do the math. 17 minus 4.5, so 12.5. Do we have a value less than 12.5? No. So we don't have a potential outlier on the left side, right? So let's get to the right side. So then our fence or our limit will be Q3 plus 1.5 times IQR. So our Q3 value is 20 plus 1.5 times 3. So we will have 24.5. So do we have an outlier, potential outlier? Yes, we do have a potential outlier. So 29 is going to be your potential outlier. So what's going to happen in that case? What you should do, basically what you should do, when you draw the box plot, you should start with the minimum, which is going to be 14, okay? Then you will get Q1, which is 17. You will get Q2, which is 19. And you will get Q3, which is 20. Then you cannot use 29. So what you do, you go up to 24. So that's going to be basically your box plot. So if 24 were not the outlier, if 29 were not the outlier, I would include that one. But 29 is the outlier. So what I should do, I just should put 29 here like this. So that's the basic idea. And this is really easy to do. I would suggest you use this approach. Okay. I think the book has used a different approach. But one thing really good about box plots, when you have box plots next to each other. So this is for female, and then this is for male. As you see the Q1. Let's do it like this: Q1, Q2. I'm sorry. This is the minimum. This is Q1. This is Q2. And then this is Q3, and then this is maximum. And for male, so you have the min, Q1, Q2, Q3, and max. So when we think about the time, you see, for all values, the minimum Q1, Q2, Q3, and max, the man side is always higher than the female side. So male side is always, the time on that side is always. And then when you look at the distribution like this part, you have a distribution kind of approximately symmetric. And then here you have a distribution which is skewed. So you can understand the skewness just by looking at data. I would suggest that you draw the box plot like this. Then you will have, actually, it's going to be easier for you to interpret the data if you draw the box plot horizontally. But if you do it vertically, it is a little bit difficult to see what the trend is. Right? You see, a potential outlier is here. So you know what the basic idea is, right? You see, they did the same thing. Okay. There are some different box plots, but you got the basic idea. It's going to be easier when you understand the concept. It's going to be much easier. But box plots are a great way of showing the comparisons between two data sets. So let's look at bar charts. You see number of buyers and previous computer, Windows and Macintosh. As you see the bar charts, the trend is easy to see. Okay. I mean, we can draw different kinds of bar chart, like this one is percent increase or percent decrease. Just the idea is different. But the core principle is the same, you see. The core principle does not really change. So we can look at the line graphs. Okay. You see those are the years, right? Actually, July 2000, October 2000, January 2001, and then April 2001. Actually, these line graphs are best for time series. So line graphs are best for time series. And then this is the line graph of the percent change in CPI over time. Okay. The same idea. Okay, line graphs are appropriate only when both X and Y axis display ordered, right? Ordered data, like time series, like, you know, July, October, January, April, you see it goes like this. So it is going to be ordered, okay? Although bar charts can also be used in this situation, line graphs are generally better at comparing changes over time. You know, for some graphs, it is not easy to interpret, such as this. So, okay, we can have misleading graphs anytime, so we should be really careful about it. Let's check the dot plots. You see, in dot plots, you have different colors of M&Ms. You may remember this question. Okay, so brown, how many? This many, right? Green, this many. Red, this many. Orange, this many. Yellow, this many. And then blue, this many. So only 3 blue M&Ms. Whereas like for brown, we have 90. So this is called dot plot. Okay. Is a different one, like you know, in that case, the categorical variable put here, and then that is the number. It really doesn't matter. As long as the basic idea is okay, you can do either way. Okay? So that's the dot plot. So when you graph distributions, as you see, this is the December, September, March, June. So what is happening? Job loss by quarter. So job loss increases, right, as time increases. So economy is not doing good, right? Basically, when you look at this one, the economy does not look good or is not doing good. It says there are major flaws with the Fox News graph. The first, the title of the graph is misleading. Okay, job loss by quarter. Okay. Although the data show the number unemployed, Fox News graph is titled job loss by quarter. Okay. Second, the intervals on the x-axis, right, are misleading. There are 6 months between September 2008, March 2009, and 15 months between March 2009 and June 2010. So intervals, right, their lengths are not the same. So you will have a false impression. So we should really be careful, you know, when we look at the data. Number of unemployed for selected quarters like December September, March, and June. This is number of employed people. Unemployed people, I'm sorry. Okay, we kind of covered how we can, make comparisons or how we can draw the graph. Okay. Let's solve a couple of questions here. Based on the frequency polygon displayed below, the most common test grade. The most common, as you see, this is the frequency, and this is the test score. The most common means the score must have the highest frequency. So where is the highest frequency? Here, right? You see the peak, the highest frequency. So when you draw something like this, so it means it's gonna be the most common grade, which is called the mode, will be 85. Okay. Okay, and so this one in a box plot, what percent of the scores are between the lower and upper hinges? So lower and upper hinges, basically, the lower one, Q1, and upper one, Q3. So from Q1 to Q3, Q1 is 25th percentile, Q3 is 75th percentile. So the difference is going to be 50%. So the answer is going to be 50% here. Okay. Okay, those are some other graphs. So we will have some sessions to solve the questions, but I just solved a couple of them randomly. We can start chapter 3 a little bit. Chapter 3 is an important chapter. It's about summarizing distributions. So when we summarize the distributions, we need to talk about the central tendency. So what is central tendency? How can we measure it? Median and mean, additional measures, comparing measures. We can also talk about variability of the data. So we have measures of variability. We can have the shape, effect of transportation, and variance sum, law 1. Okay. So we are talking about basically descriptive statistics. As we covered before, descriptive statistics is about summarizing the data. Summarizing the data. Okay. So we want to see where the distribution is, where the center is basically. So when we think about central tendency, okay, let's see how can we get the central tendency. So you see you have 3 different data sets here. Okay. Okay. Definitions of the center, balance scale. This is kind of different distributions. Okay. Some of them are balanced, some of them are not balanced. Okay. Okay, let's get back to the measures of central tendency. We would like to calculate the mean, median, and mode. Okay. Arithmetic mean is the most common measure of central tendency. Simply the sum of the numbers divided by the number of numbers, right? And the symbol mu, very important. So this is the Greek alphabet. Why? Because this is for the population mean. So we use mu. The symbol m is used for the sample. So we will, and in some other books you may see x bar or y bar. So don't get confused, when you see something like that. So this is but the basic idea for the population parameters, we use Greek letters. For the sample statistics, we use Latin letters. So M is Latin too, right? So we can use M or X bar or Y bar. So the mu, which is the population mean, what you do is you add all the X values up divided by number of X values. So the formula for M is essentially identical. There will be no difference. So the only difference, you see the sample size here. This is the population size. But when you have the M, what you will have, you will total of X divided by N. So N is going to be sample size. Exactly. Here they use the same nomenclature. Okay. Okay. Table 1, number of touchdown passes. You see, this is the number of touchdown passes by, I think, 31, right? 31 teams. So when you add them up, you have 634 divided by 31. So you have 20.45, which is going to be the mean number of touchdown passes thrown. Do we just have the arithmetic mean? No. There is also like the geometric mean or harmonic mean, but what is happening basically, arithmetic mean is the most used one. The median, it's also a frequently used measure of central tendency. It is the midpoint of the distribution. Okay? So when you have 31 scores, what you do, you rank them from smallest to largest. Okay, so it means when you have 31 scores, you have a physical midpoint, which is going to be 1 plus 31 divided by 2, which will give you 16. So the 16th score is going to be your what? Median. 16th score is going to be your median. So what's going to happen when you have 32 scores? So in that case, when you have 32 scores, so you will have the 16th value, right? 32 divided by 2 is going to be 16th value. And then which one, the other one, you will have 17th value. You add them up, divided by 2. Let me give you a small example. You have 2, 3, 5, 9, right? So let's get the median here. So to get the median, do we have a midpoint here? No. What we have, 3 and 5. So the midpoint here is, so what you do is 3 plus 5 divided by 2, which will give you 4. So when you look at the formula, so when you have just 4 values, 4 divided by 2, so you will get second value plus the third value divided by 2. So that's what we did. 3 plus 5 divided by 2 will give you 4 as a median. So what if you had another value, which is 10? So what's going to happen? You see now you have the midpoint. So midpoint is going to be number 5. So the median is going to be 5 in this case. I hope it is clear. I hope it is clear. Okay. Exactly. That's how you do it. We have 4 values, 2, 4, 7, 12. So 4 plus 7 divided by 2, 5.5 will give you the median. Just be careful whether you have odd number of observations or even number of observations. How about the mode? Mode is the most frequently occurring value. Okay, here in that case, do we have a mode? No. No mode. Why? Because no value is repeated, right? You have 2, 4, 7, 12. So every value is just repeated once. So if you want to have a mode, you have to repeat the values at least twice. So there is no mode in this case. Okay. Okay, we may have group frequency distributions. Things are going to be different a little bit in that case. Okay. Okay, let me see whether they get into that or not. Okay, I didn't get into it. I can show you how we can get. I did. We can just finish this. Okay, when you have grouped frequency distribution, let's get median, mode, and arithmetic mean in this case. You see, in grouped frequency distribution, where you have the lower value and upper value. So what you do is you find the midpoint. So 500 plus 600 divide by 2, 550. 600, 700 divide by 2, 650. 700, 800 divide by 2, 750. 850, 950, and 1050. 1050 or 1050. Okay, so you have the MI values and the frequency values. Okay, let's get the arithmetic mean. Since you have frequencies, let's call them is f of I times m of I divided by total of f of I. So let's do it. 550 by 3 will give you 1650. Okay, 650 by 6 will give you 3900. 750 times 5 will give you 3750. 5 times 850 will give you 4250. This is going to be 0. And then this one is going to be 1050. So we add them up. Let's do it. 14,600. So that is the denominator, 14,600. And then let's add the frequencies up. 3, 9, 14, right? 19, 20. Okay, so we divide this by 20. So you get arithmetic mean. Let's call it for the sample M, which is going to be 730. So how about the median? So for the median, since we have 20 values, so you need to get the 10th value and 11th value. So 3 plus 6 will give 9. Okay, you see. Then you have 10, 11, 12, 13. So you have, just put it like this. So you have 550, three of them, right? And you have 650. How many of them? 1, 2, 3, 4, 5, 6. Okay. And you have 750, 5 of them. 750, 750, 750, 750, 750. Okay. So it goes like this. Okay. So what is the 10th value? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10th value is 750. So what will be the 11th value? 11th value is another 750. So divided by 2, which will give you 750. So our median for this data set will be 750. Okay. How about the mode? So mode is the Y value with the highest frequency, right? So where is the highest frequency? Highest frequency is here, 6. So it means our mode is going to be 650. One more thing before we, finish the class today. You can decide the skewness based on this data. So which one is bigger, median or mean? So in that case, median is bigger than mean. That's why this data is left skewed. Okay, everyone, that's all for today. I wish you very good day and very good week. See you later. Bye.